So as that rock is rolling through the tunnel, is it making a lot of noise? I mean, they did a great job of the sound engineering and sound effects of that. Okay, making a lot of noise. Noise is a product of?
Force.
Which force? Friction, yeah. Okay, so as we can see here, we got that stone, we're going to say it's 400 kilograms. Okay, from a physics perspective, what height would the rock have to drop from if it rolled 30 meters against a frictional force of 800 newtons and it was moving at 4.5 meters per second when it sealed shut the temple? So we can simplify this. We don't have to draw a tunnel. I mean, obviously it changed directions a few times, but when it comes right down to it, okay, it's really just an inclined plane, right? Because it had a ramp, right? It didn't fall out of the ceiling, it rolled out of the ceiling, okay? So really, we're just looking for the height that it started at. All right, I'll give you a bit of time, see what you remember from yesterday. Okay, so let's just kind of talk this one through here. If there was no friction, the initial energy of the rock at the top and the final energy of the rock at the bottom would be equal. Agreed? It would be a law of conservation of energy question then. But it tells us outright, no, there is friction. We watched the video, we could hear the noise. Okay, there was definitely friction involved. Friction works against you. It takes energy away. So in this case then, friction is the reason why work is being done and why the rock has less energy at the bottom than it does at the top. Okay, so the less part is important. Right, we know that the rock is 400 kilograms. Okay, top and bottom here. Now, the force of friction is 800 newtons, and that acts over a 30-meter distance. So work is definitely being done. So I can say that work will be the change in mechanical energy. That work is going to be negative, so I do have to remember that the force of friction is a negative number. So force of friction times distance is going to equal, okay, the final potential plus the final kinetic, okay, minus the initial potential plus the initial kinetic. Now, two of those are zero. Which ones?
The kinetic initial and the final.
Right. So that one's zero because it's not moving at the beginning, and since we're at the bottom, that one would be zero because our final height would be zero. Okay, so what this comes right down to is that the force of friction times distance, the work being done by friction causing the rock to lose energy, is the final kinetic minus the initial potential. Now, what I'm looking for is the initial height, which would be part of the initial potential energy. Agreed? Okay, so if I want to get the initial potential by itself, I would move it to the other side. Because right now, I'm subtracting it. I'd like it to come out positive. So I'm going to move it to the other side. Okay, by doing this, I'm going to go EP initial plus FFD.
Please excuse the interruption. Could we please have the Model UN, Fine Arts Council, Board Game / Crib Club, and Faith and Fellowship Club down to the cafeteria for your photos. Thank you.
That's in, you guys go ahead. All right, now I'm going to bring the work over here. Final energy minus the work should give me the initial. All right, so. Okay, so here's how I get the positive number. Friction is negative. When I subtract the negative, I get a positive. That will make the initial potential bigger than the final kinetic, which it should be. All right, so I will have m times g times h initial equals 1/2 mv final squared minus the force of friction times distance. Okay, I still need to isolate the initial height. So what do I do with m and g? Divide them over the other side. Okay, now I'm solving for initial height. All I have to do is plug in my numbers. So initial height will be 1/2 times 400 kilograms times 4.5 meters per second, all squared, minus 800 newtons times 30 meters, negative 800 newtons, divided by 400 times 9.81. Shoot, I forgot to start that up. Okay, so we'll have our 0.5 times 400 times 4.5 squared. Okay, so there's our final kinetic energy, our final mechanical energy, actually. Okay, minus negative 800 times 30. All right, so there is my initial potential energy. It's a much bigger number than the final kinetic. Now I divide that by 400 times 9.81. Okay, that's a pretty reasonable answer. Remember, Harrison Ford is nearly 2 meters tall, and he looked way up above him when he heard the sound of the rock. Okay, that could easily have been another 5 meters up from there. Okay, obviously not all that stuff really happened, but he does a good job of selling it because he's a good actor. Okay. All right, making sense? Okay, so work energy theorem is a big deal, not just in in terms of like physics, but in terms of real world situations that you could be in. Okay, how many people have ever seen an avalanche? Okay, I mean like close up or from far away? Close up?
Pretty close.
Pretty close? Yeah, like it's not what like video you've seen of an avalanche looks like or feels like. You feel an avalanche as much as you see the avalanche. It rumbles, okay, as all of that snow comes rolling down the mountainside. Is there still a lot of friction between the snow and the mountainside? There is. That's why it's so loud. It's what eventually causes the avalanche to slow or grind to a stop, okay? But in the meantime, can it pick up a lot of kinetic energy? Yeah. They don't generally stop until they've been going along a flat valley for a while, okay, or they run into another cliff face and are forced to a stop, okay? But people don't give them enough respect. If you've ever seen one, you'll never not respect one again if you've ever been up close, okay? But to kind of show you this video I saw this morning, it got me thinking about this question and work energy theorem when it comes to avalanches, okay? We know that if you have a lot of mass and a lot of speed, you have a lot of what kind of energy? Kinetic. Okay, that's why avalanches can be so dangerous, is because they're carrying not just a great amount of mass, but also a great amount of speed. Okay, and they get that because they have fallen from a very high height. 10,000 meters is where that avalanche could have started. Right, that's a long way to fall. Imagine something building up energy as it comes down 3 or 4 or 5 vertical kilometers. Okay. They had this happen at Everest Base Camp a few years ago, and it wiped out the camp. They actually got all the way there and took everything out. Okay, and I'm pretty sure a few people died even in it. Okay, so it's a big deal. It's a lot of energy that's there, and it can do a lot of work. Okay. All right, that was the other thing I wanted to show. Okay, so give that one a try. Okay, you got a 90 Newton box. Okay, pulled 10 meters along a level surface by a rope, but the rope is angled 20 degrees above the horizontal, okay? And the force exerted through the rope is 75 newtons, okay? How much work is done on the box? Okay, pretty simple question. Don't overthink it.